In this video, we're going to talk about two applications of integrals. First, the length of a curve, and second, the area of a surface of revolution. So first, let's look at arc length. So we have a function going along the x-axis from x equals a to x equals b. I want to know how long the graph of that function is, and that's called arc length. We're going to assume that our function is what's called smooth, which means that the derivative of f prime, is continuous at all the values of x on the interval from a to b. The simplest curve is a straight line, and we don't need calculus to find the length of a straight line. You can use geometry to find the length of a line segment. And anything that's not a line, we're going to use line segments as an approximation. So here's the general idea of finding arc length. We take our interval from a to b along the x-axis. We divide it up into n subintervals of equal width. I'll label the endpoints just like we always do. X sub 0 will be a, x sub n will be b, and all the intervening ones will be x sub 1, 2, 3, etc. We're going to find the length of the line segment that connects the points that go on the endpoints of the interval. So here, this first interval goes from x0 to x1. So we'll take x0 and f of x0. That will be the starting point of our line segment, and then we'll take x1 and f of x1, and that will be this end point of our line segment. We'll just connect those two points on the graph of f, and we'll find out how long the line segment is that connects them. And then we'll do the same thing. If we go from x1 to x2, we'll just connect dots with a straight line and find the length. Add up all the lengths of all those line segments to get an approximation for the arc length of the curve f, and then take the limit as n goes to infinity to get the actual arc length. So here's a sample when we have four subintervals. So x sub 0, here's a where I'm starting, here's x1, so I'm going to approximate this curve here with this straight line from x1 to x2. I'm going to approximate this curve here with this straight line from x2 to x3. I'll approximate this curve with this straight line from x3 to x4. I'll approximate this curve with this straight line. And you can see this is, especially here, the curve goes all the way down here, and the line just kind of cuts across there. It's much shorter. So this would not be a great approximation, but that's only n equals 4. So if I make n bigger, then I would get a better approximation. Okay, well, that should sound familiar. Dividing up into n equals subintervals and approximating and then adding them up, taking the limit as n goes to infinity, we get an integral at the end. So let's see what this integral is going to look like. So what is the distance between these 2 points? So if I'm looking at the from x sub I to x sub I plus 1, it might be 0 to 1 or 3 to 4 or whatever it is, how far is the line segment that connects those 2 points? I'm going to call that L sub I. Well, you just use the distance formula. The distance formula, when you're talking about ordered pairs, it says you take the square root of the difference of the x-coordinates and square that, and then you take the difference of the y-coordinates and you square that. You add those two together and you take the square root of the whole thing, and that's the distance between those 2 points. Now the change in x here is the constant because all our subintervals have equal width. I'm going to call that delta x, and that's equal to b minus a over n, just like it always has been. Now what do we do with this other part here where we have the difference in the y-coordinates? This is where things get a little bit nastier. So if you remember the mean value theorem from calculus 1, there always exists and some number, I'm going to call it c sub I, in this interval, okay, between x sub I and x sub I plus 1, there exists this number c, so that the derivative of f, evaluated at c sub I, is equal to the difference in the y-coordinates over the difference in the x-coordinates. That is, this is the slope of the secant line. This is the slope of the thing here on the right, is the slope of that line segment we're talking about. And the mean value theorem says anytime you have a secant line, the slope of that secant line is going to equal the slope of some tangent line, which is the derivative. So there's some number c where the slope of the tangent line equals the slope of the secant line. Now we just multiply both sides of this equation by delta x, and we get the change in y-coordinates is equal to the derivative somewhere, we don't know where c sub I is, but somewhere in this interval, the derivative times delta x gives us the change in y. Okay, so let's put that back up here in our L sub I with a distance formula. We're going to replace the change in y coordinates with this derivative times delta x. So there it is. And notice here we got derivative squared. We have delta x squared. Here's another delta x squared. So I'm going to factor out the delta x squared. So there it is. You factor delta x squared out of this guy and you have 1. You factor delta x squared out of this guy and you have the derivative squared. Okay, and I'm going to break up this square root into 2. So I'm going to take the square root of delta x squared, and delta x is positive, so that square root of delta x squared is delta x. And then you're taking the square root of 1 plus derivative squared. Okay, notice this delta x here in the end is not under the square root. I took the square root of delta x squared, it canceled the squared, and I got just delta x. Okay, so add those all up. As I goes from 0 to n minus 1, you add up all these L sub i's, and that gives you an approximation for the total arc length. You take the limit as n goes to infinity, so you get the actual arc length. And so L sub I is this guy, and this thing right here in the middle is the Riemann sum. It's a limit as n goes to infinity of a sum of n things where you have a function times delta x. That's the Riemann sum, and that means that limit is an integral from x equals a to x equals b. The delta x becomes our dx, and this c sub I becomes just x. So this is our arc length formula. And oh, by the way, this is why we assume that f prime was continuous at the beginning. That means this limit will exist. So here's the moral of that story. We get the arc length formula. If a function has a derivative that's continuous on the interval from a to b, then the length of that function f from x equals a to x equals b is the integral from a to b of the square root of 1 plus f prime squared, and that's it. Now this integral can be pretty nasty to compute. This is kind of a nasty thing here with square roots, but we'll see there's a few of these you can do by hand if you had particular functions. We'll let Sage do these for us. We might have to use numerical integral if the integral command can't integrate it, which is possible. So here's an example. Gave you a function, natural log of secant of x, from x equals 0 to x equals pi over 4. So I want to find how long that is. Well, here's my formula. So first I need f prime. So there's f prime. The derivative of natural log is 1 over whatever's inside, so that's 1 over secant. The chain rule says take the derivative of secant. The derivative of secant is secant times tangent. Notice that these secants cancel and you end up with just tangent. So f prime is tangent. Alright, so the formula says take the square root of 1 plus f prime squared. So square root 1 plus f prime squared, f prime is tangent, so we get tangent squared. 1 plus tangent squared is secant squared. That's one of the Pythagorean identities you learned in trigonometry. The square root of secant squared is the absolute value of secant. And because x is between 0 and pi over 4, secant of x is positive, so the absolute value of secant is secant. That means this thing here inside the arc length formula, all that simplifies to secant. So this arc length is the integral from 0 to pi over 4 of secant of x. And that integral is known, not a nice one, but it is known. This is the integral of secant. The natural log of the absolute value of secant x plus tangent x. And then you plug in the numbers and simplify, this is what you get, the natural log of the square root of 2 plus 1. Now if you ask Sage to do this, so here's my function f, I want to integrate, not f, what I want to integrate is the square root of 1 plus the derivative of f squared. So integral of the square root of 1 plus the derivative of f squared. And there's the end parentheses for my square root. The integral is with respect to x, and it's a definite integral from x equals 0 to x equals pi over 4. Now the answer that Sage gives me is this hyperbolic arc sine of 1. Now this is not arc sine, the inverse sine function. This is this little h here says this is the hyperbolic arc sine. You probably haven't seen that function before. It really doesn't, you don't need to know about it. It is in fact equal to this. So if you ask Sage, what is the hyperbolic arcsine of 1, convert to a decimal, and take the natural log of square root of 2 plus 1, convert that to decimal, and they're the same number. Here's what happens if you simplify first. So all this work we did up here to simplify this all down to secant, if you do that yourself and just integrate secant, this is the answer that Sage gives you, which is also the same number, though it looks quite a bit different. Not sure exactly how things turned out that way, but we could probably simplify this if we did some algebra on that thing and it would work out. Alright, here's a second example. Find the length of 1/8 x squared minus the natural log of x from x equals 1 to x equals 2. So we take the derivative of this guy. The derivative of 1/8 x squared is 1/4 x. The derivative of natural log is 1 over x, and so this is f prime. So we need to integrate from 1 to 2 the square root of 1 plus this derivative squared. And it is possible to do this one by hand. You can expand this squared and add one, kind of combine fractions, and you will see that there is some simplifying that can do it. It is possible, but it's kind of a mess to do the algebra. So we'll just let Sage do it. So here I define the function. Integral square root 1 plus derivative of f squared. This is the arc length formula. You can just copy and paste this guy if you want to. All you need to do is change these limits of integration. So that doesn't change. The formula doesn't change. All it changes is f, and then these numbers here at the end. So there's our exact value, log of 2 plus 3/8, or about 1.07. And remember, this log in Sage is the natural log, not log base 10. Oops. So, example 3. Find the length of this parabola from x equals 0 to x equals 2. So, what's the derivative of this quadratic? It's 6x minus 5. So, my arc length is the integral from 0 to 2 of the square root of 1 plus 6x minus 5 squared. And let's let Sage do this one. So, here's my function. Here's the arc length formula. I change the limits of integration, and I get the length of roughly 6.7. And notice if I look at the exact answer, I have square root of 26, square root of 2, and here's that hyperbolic arcsine again. So it's kind of a messy answer. Okay, here's the cosine function from x equals 0 to x equals pi. The derivative of cosine is negative sine. So I want the square root of 1 plus negative sine squared. The negative cancels out in the squared, so I don't really need to put the negative there. Looks simple enough, except if you try that integral in Sage, you get a big error message. And it says runtime error, error executing code in maxima, which is a long way of saying I don't know how to do that integral. So this one we'll have to use a numerical integral to get an approximation instead. Remember the numerical integral command, you just numerical underscore integral, you do the function and then the lower limit and upper limit. You do not specify the variable of integration like you do in the regular integral command. That's because regular integral command does things algebraically. It allows multiple variables involved, so you have to tell it which one is the variable of integration. This little one, the dx indicates that it's x. With numerical integral, the answer needs to be a number, so there can be only one variable involved, which is automatically the variable of integration. So you don't specify it. So here's numerical integral of the same thing. This is the answer, remember. You can ignore this second number. Just gives you an idea of how large the error is in this approximation. So it says the error is somewhere down in the times 10 to the negative 14 zone, which is pretty small as far as we're concerned. So 3.82 is a good approximation. Okay, so there's some arc length examples. I want to do one more application of integrals in this video. That's area when you have a surface of revolution. So we talked about volumes of solids of revolution, but instead of rotating a plane region, like the area between two curves or the region under the graph, between the graph and the x-axis, we're just going to rotate the curve itself. And we're not going to get a solid. What we're going to get is the surface. It's like the boundary, the outer shell of the solid. And we want to get the surface area of that thing. Okay? So I'm not going to go through every single bit of algebra that is involved in doing that. We saw how you get the formulas for volume and for arc length, and it's similar kind of stuff that goes on. So we have a curve. I'm going to assume my curve is positive, so above the x-axis from x equals a to x equals b. I'm going to rotate that curve around the x-axis to form a surface. I'm going to divide my interval along the x-axis from a to b, divide that into n subintervals of equal width, label my endpoints in the normal way. For each subinterval, I'm going to approximate the curve with a line segment, just like we did with arc length, but instead of finding the length of that line segment, I'm going to rotate that line segment around the x-axis. And what you get when you do that is what's called a frustum of a cone, a piece of a cone. So it's like a cone with the top chopped off. And the surface area of a frustum of a cone is known from geometry. Here's the formula for surface area of that piece of a cone, 2 pi times y times L, where L is the length of the line segment, that it's the slant height of the thing, and y is the average height of the line segment above the x-axis. That's the average radius of the frustum. Okay, so it's a cone, so it's sloping in. So the radius of on the bottom of this piece of the cone is bigger than on the top as it slopes up. So you're going to take the average radius of the cone and then the length of this along the slant side. All right, so to get the surface area, you add up the approximations from each subinterval. You take the limit as n goes to infinity. You do some messy algebra. You have to do something with the mean value theorem, similar to what happened for arc length. I'm going to skip over that. You can read about it in your textbook if you really want to know. But it's similar kind of ideas that we've already seen. What comes out is this formula. And this should look familiar. Square root of 1 plus f prime squared. That's the arc length formula. And then we have this 2 pi times f. And as you kind of compare that to this, it's 2 pi times the y value, which gives you the kind of the radius of your cone, and then times L, which is the length of the side. So that's the same thing we see here. 2 pi, the y value is given by the function itself. So, and then the length is given by the arc length formula. So it's like 2 pi y times L. It's just this geometry formula kind of converted into calculus so that now we can do curves. Okay, again, I'm going to assume that f prime is continuous from x equals a to x equals b, which will guarantee that this integral will exist. Okay, let's go ahead and use this formula in an example. Find the surface area of a sphere of radius r. Now that surface area is known from geometry. You don't need calculus for that, but let's make sure that the answer agrees. So here's our surface area formula. We need a function that will give us the sphere as a surface of revolution. And the thing to use is this thing, the square root of r squared minus x squared. That is the top half of a circle. And, a semicircle centered at the origin of radius r. That's the top half of the circle. If you rotate that around the x-axis, you will get the sphere centered at the origin of radius r. Okay, the derivative of this thing is that guy. And so we plug those all into this formula. X goes from minus r to r, so that's the limits of integration. We got 2 pi times the function itself, which is that ugly square root thing. Square root 1 plus, here's the derivative, all squared. Okay, so when you square this thing, where did this r come from? Yeah, sorry, I saw this x here and I was expecting x squared and then I saw r squared. That's because I added the 1. You had to combine these two fractions, and that's why I was messing myself up. I skipped a step here. You square this, you get x squared over r squared minus x squared. And then when you find the common denominator, which is r squared minus x squared, the x's cancel out and you're left with r squared. Sorry about that. I skipped a step and tricked myself. So anyway, this square root of r squared minus x squared cancels this square root of r squared minus x squared, and you're left with 2 pi times the square root of r squared. R is positive, so the square root of r squared is r. So you end up with the integral from minus r to r of 2 pi times r with respect to x. So this is a constant. So this is an easy integral, and anyway, there's the answer. 4 times pi times r squared is the surface area of a sphere. And here's the three-dimensional picture, which again I can't manipulate without freaking out my computer here while I'm recording. Here's the calculation in Sage. If you are rotating around the y-axis, then you may use x as a function of y. So if you're given a function g of y that specifies x equals g of y, g prime is continuous from c to d, where that's an interval of y values. The area of the surface that you get by rotating around the y-axis is this guy. It looks exactly the same as the one before, but instead of a to b, I have c to d. I changed the letters here just to emphasize that these are y values. So this is an interval on the y-axis. 2 pi times your y function, 1 plus the square of the derivative of that y function with respect to y. Now it's also possible to do this in terms of x. So if you're not given a y function, if you have an x function, you can convert it to a y function and use this first formula, but you don't have to. It actually works out nicely, which I won't prove, but take my word for it. You can use the x function, f here. The only thing that changes is that now the radius is given not by the function, but by x itself. Okay, so compare this to what we had up here, rotation around the, where's that formula? Oops, went too far. Sorry about that. Here it is. This is rotation around the x-axis, and it's 2 pi. The radius of the cone is given by the function. Okay, so the cone is sitting on its side. I'm rotating around the x-axis, so I have the cone sitting on its side. So the y value gives me the radius, and then you have the length. In this case, when I'm rotating around the y-axis, the cone is, here it is, the cone is sitting upright, like the way we expect it to. The radius is now given not by the y value, but by the x value. So you can just put in x here. 2 pi x, and then this is the length one. Okay? Use either one of these formulas depending on what you're given. If you're given a y function, do everything in terms of y. If you're given an x function, there's no need to convert these to y like we had to do with some of our volume examples. You can keep x. Just remember, this is x, not f of x. Okay? Find the area of the surface generated by rotating around the y-axis, the graph of f of x equals x squared, from x equals 0 to x equals 2. Okay, I'm going to show you that both of these formulas do give you the same answer. So first off, let's go ahead and convert all of this to y functions, and this is the long way, but that's okay. I just want to show you that it does work. So we can convert this function, y equals x squared, convert this to x equals square root of y. Notice here we're dealing with positive x's and y's because x goes from 0 to 2 and y is going to go from 0 to 4. Okay, so x is the positive square root of y. This interval in the x-axis from 0 to 2 corresponds to the y interval from 0 to 4. So if we're doing everything in terms of y, our limits of integration need to be y numbers. So it's not 0 to 2, it's 0 to 4. The derivative of this square root of y function is 1 over 2 square root of y. So we get this guy, and that integral, I won't show you the details, turns out to be pi over 6 times 17 root 17 minus 1. Okay, go figure. Since we're given an x function to begin with, it would have been easier if we didn't bother with all this changing to y stuff and just did everything in the x direction. So x goes from 0 to 2. The derivative of x squared is 2x. And then you don't put the function f here. You don't put x squared. You just put plain old x. Okay, that's the difference when you're rotating around the y-axis and you have an x function. It does turn out to be the same thing. Here you can see in Sage, they do turn out to be the same thing whether you use the g of y or use f of x. They're both roughly 36. And here's the picture of that surface. All right. I think this is our last example, Gabriel's horn. So we're going to rotate around the x-axis the graph of 1 over x for x greater than or equal to 1. So there's no upper bound here. So the area of the surface is the integral from 1 to infinity of 2 pi times the function. Okay, we're rotating around the x-axis again. Okay, so it's the function, 2 pi times the function. Square root of 1 plus the derivative of 1 over x is minus 1 over x squared. So that guy's there. Now, that, we don't need to figure out what that integral is. This is an improper integral because of this infinity. We want to see if this converges or diverges. It actually diverges. We know that because this part here, the square root part, is greater than or equal to 1. Okay, that's what I said right here. Because you're taking 1, you're adding something positive. Okay, there's a minus sign there, but remember this is squared. So 1 over x squared is something positive. So 1 plus something positive is bigger than 1. You take the square root of that, you get something bigger than 1. So this guy is bigger than 1, which means this whole mess is bigger than that. I'm replacing the whole square root mess with 1, and I'm getting a potentially smaller integral. Integral from 1 to infinity of 2 pi over x is a divergent improper integral. We already saw that 1 over x diverges as you go off to infinity there. So this is a divergent integral. This one is bigger or equal, and so it must also diverge. So the surface area is infinite. And the reason I'm doing this example, it's kind of a freaky paradox that the volume of Gabriel's horn is finite. So here's our volume formula. We use the method of disks. It's just pi times the radius squared, the radius given by the function 1 over x. So this is the integral from 1 to infinity of pi over x squared, which actually converges. And the answer is pi. So this thing has volume pi, but infinite surface area. So you can fill the horn up with paint. If you have pi units of paint, you can fill the horn up. Cubic units, I guess. But you can't paint the surface of it. Strange. Don't think about that too hard. So here's a piece of the horn. You got to imagine this horn goes off to infinity. The mouthpiece here gets smaller and smaller and smaller, which is why it's called Gabriel's horn. He being an angel, he can have, I guess, his mouth at infinity and blow on this horn. I didn't make up the name. Okay, so there's some examples of arc length and surface area.